Swayam Prabha. Digital India. Educated India.
We will move on to the determination of shear stress transmitted by the beam. And you will find how comfortable it was to take up a beam transmitting only bending moment, discuss the deformation, and evaluate the axial strain developed. The moment you come to determination of shear stress, you need to perform experiments very carefully. As I have always emphasized, doing a thought experiment or a direct physical experiment. And what we will do is we will do some nice experiments and make clear observations on what all things that happen when we apply the load. For our discussion, we will take up a problem of a 3-point bending, and you know how to draw the shear force and bending moment diagram. And what we have done here is we have introduced a constant shear force. Earlier we had only constant bending moment transmitted by the beam. Now I have a constant shear force. Even if I add a constant shear force, my bending moment varies linearly. And without proof, I have also shown you how the section will change in the presence of a shear force. We have made certain observations like the plane section gets distorted like this, and what you have is here the original 90 degrees preserved, so which indicates shear strain is 0, which we have also seen when I have this as a free surface. Even though I may have a shear force transmitted by the beam, the distribution which you evaluate from strength of materials should be such it has to be 0 at the top point as well as at the bottom point. That we have understood from the discussion on free surfaces. And we also note that you have a maximum change in the angle at the middle plane, which is coinciding with the neutral surface. So your shear strain or shear stress reaches a maximum here. And even though my bending moment varies along the length of the beam, in engineering analysis, you use the flexure formula, and in that you use the bending moment as what is seen at that particular length of the beam. That is the way that we would use the flexure formula developed primarily for a beam which transmits only bending moment, constant bending moment. So even when the bending moment varies, we invoke the same formula and substitute this bending moment. And let us do some interesting experiment. I am going to have a beam which is made of perspex and it has some thickness, okay. And I am also going to do the experiment on 4 simple strips which when you put together it forms the thickness of the beam. In fact, this is also added as one of the experiments in your strength of materials lab long time back when I introduced this. I am not sure how carefully you have done the experiment. I said if the experiment is done carefully, it is truth. So whatever the theoretical development that we make, it should explain what is observed in the carefully done experiment. Let me add that adjective. You have to do the experiment very, very carefully. I have the beam subjected to 3-point loading, and the second case is, when I put this, I also find out the 0 load, what is the, I have also put the scale, and you can carefully see that this is about 217 millimeters. The idea is when I am going to change my beam, I am going to look at what is the deflection that is created by the same load. Supports are same and your load is also applied is also same. We are going to investigate. The case 2 is a layered beam. When I add the thicknesses, it adds up to the thickness of the original beam. And the third case, what I am going to do is, I am also going to tie these layers. So that means they are not allowed to move freely. I have 4 pins, but I will just insert 2 of them to illustrate that I am not allowing them to have any relative motion. Just to understand what way the experiment shows up. So the third case is I have a pinned layered beam. Okay. So let us do the experiment. And zero loading is put as 217 millimeters. And then I have, when I apply the load, it gets deflected. And now the deflection is 218. So it has deflected only by 1 millimeter. It's very, very small. When I have the perspex beam, when I put the load, see, it's not as flexible like the plastic beam, it's very strong. Okay. And you have a deflection of only 1 millimeter. Suppose I put the load on the layered beam. You find that it has deflected to 246 millimeter. That is the scale reading. The initial reading is 217. And I find that the deflection, what you find is very large. It's about 29 millimeters. See, yesterday I said I have to double the load carrying capacity of the glass plate. And I said from a design perspective, I can make multiple options. One option is to buy another glass plate, put on top of it. Another option is increase the thickness of the glass plate. The third option was put one more support. After this experiment, what would you say about putting another glass plate? It's not found to be effective. Let us see if I pin them, what happens? That means I am restraining it. Okay. And when you find this, the deflection is 239 millimeter. These are all very carefully done photography, because if you look at this, it's not just the figure is shown, you also see the reading from the scale to convince you. And you find the deflection is reduced compared to the earlier case by about 7 millimeters. This is 22 millimeters and this is 29 millimeters. Whereas if I have the solid beam, that had hardly any deflection. See, for the purpose of illustration, what happens when I have a layered beam? I have taken 4 layers. And if you really look at the beam, I can imagine infinite layers of very thin cross section, very thin depth. And even when I do the pinned case, I have just put 4 pins. Suppose I had put instead of 4, if I had put 10 pins, then what would you anticipate? This deflection would be still smaller. So the beam becomes and behaves more and more stiffer. So something is happening in the beam. So we'll have to find out, our interest is to find out what happens in this solid beam. To appreciate what happens in the solid beam, we have taken layers to understand what happens in between the layers. Because this is very subtle. The issue what we discussed today is a very subtle concept. And you can also make a record that y1 is the least, y3 comes in between, and y2 is the largest deflection. And this is a summary. I have 1 millimeter, and then in the second case I have this as 29 millimeters, and in the third case you have this as 22 millimeters. See, even before we take up a deflection, these slides illustrate when I have a 3-point bend specimen how the beam is deflecting. You know, you have to do that because we are going to study principle of superposition even in deflection, where you will have to visualize how a beam can possibly deflect. Only then you understand. See, as engineers, you have to have a lot of visualization skills. And now we would see very closely what happens at the edge. Fine. You observe this video, and what you find when I apply the load, I am showing only this portion. You could see that this is getting lifted. Fine. This is for a homogeneous beam. Now I have a layered beam. So you have this only like this, there is no significant change on this, this remains straight on the edge. Now I have a layered beam. Even here I only focus my attention on this and find out what happens. Okay. Can you see? There is something interesting happening. Was this edge remain straight? It does not remain straight. Okay. And what you have is, you have these layers have slipped to different extent. That is why you see this as a edge like this. So conversely, what we can understand is, something was there to keep them together in the homogeneous beam. That is the reason why this edge remained straight. That was missing when I have a layered beam. So the layered beam is free to move, and it has utilized that freedom to come out, slip between the two. And what we would do is, we would see this in a enlarged fashion, and you see this animation. You know, you have to understand this very, very clearly. And you know, you see it very clearly that when the experiment is done carefully, you find this has got shifted like this. And you really see the layers have slipped along this boundary. Make a sketch out of it. I wanted to make a sketch. It's a very important observation. I am not sure how many of you have made this observation when you did this experiment and carefully looked at what happens and why it happens. All are important. See, now what we will do is, we will also see the solid beam, how it gets deflected. You know, it has gone up. I do not know how many of you have observed. To aid your thinking, I will also draw some extra lines. So I have drawn a line where the edge is. So it has moved up like this. Suppose I repeat the animation, you can see that the beam has moved up slightly. See, when you perform an experiment, I said people do the experiment with some anticipation. You don't do the experiment blindfolded. Even before you start doing the experiment, you find out what all things have to be looked at in the experiment. Because many experiments you may not be able to repeat. If the experiment is dynamic, then you have to be very careful in recording the dynamical behavior. So you must have a pre-plan what all things that you need to note. What is key in this experiment is, you should also look at what happens to the edge. And look at here, this is the horizontal lead, to what extent this beam has got lifted. That is because this had the maximum deflection downwards at the load application point. So the beam has got deflected like this. When I have like this, it has deflected like this. Okay, so you also see that it gets slipped, but this is not a very careful experiment. See, that is the reason why I thought that I would record the video and then blow it up and then show. Is the idea clear? You are convinced that something is happening between the layers, and that we have to quantify and evaluate. And you can see very well when I have two surfaces have a relative motion like this, you call that as shear, isn't it? Fine. So, if shear stress get developed, it will try to keep the edge straight like this. Fine. And where does this come from? We have already seen that when I have a constant bending moment, the life was very simple. The moment even I introduced a constant shear force, bending moment was varying linearly. Now, we will take up a very generic case, and here the sign convention you have to follow, that is very important. And we say on a positive surface, positive shear is shown in the positive direction. And you also have bending moment varying along the x-axis, and we have shown the variation as mb here and mb plus delta mb, and I have taken anti-clockwise moment as positive. Sign convention is very important, because when we assemble the equation, you have to put them in positive sign for us to get the basic equation, and our mathematics will fix the sign automatically. So, what you find is the bending moment varies, and now if the bending moment varies, we have already said to find out the stresses due to bending, simply use the bending moment at that cross section, use the Flexure formula. That freedom we have given. Fine. So, if I go and plot what happens on the two surfaces, we know that it is varying linearly, and as the bending moment has increased, so to say, if we take this as an increase, I would have larger stresses acting on this edge, incrementally larger. Is the idea clear? Now, what I am going to do is, the beam as a whole is in a state of equilibrium, and it is a deformable solid. For a deformable solid, we have said every conceivable subsystem should also be in equilibrium. We have to investigate that. So, one of the ways to do it is, let me put a cut. Okay, I also have the shear force transmitted by the beam. So, I will put a cut horizontally, that is shown as the pink plane. So, I slice from the top a particular height and I slice this like this. Is the idea clear? I want to take out that slice. The beam as a whole is in a state of equilibrium. When I take a conceivable subsystem like this, it should also be in a state of equilibrium. So, let me draw this, and I have always been saying, when I want to illustrate, suddenly I will put things very large, so that we see what happens in that section. Never forget, we are handling only slender beams. For illustration, we are doing it. So, whatever we have understood from this, we will translate as forces acting. To make our mathematics clear, we have identified this section, what I have put is at a height of y1, and I put a horizontal section, and the element is delta x. So, I have bending stress indicated on this face and bending stress indicated on this face, and it is also put for the entire width of the beam. I have this, please make a neat sketch, that is the reason why I am going slow. These are all conceptual understanding, and if you understand how we arrive at the shear stress distribution, you will know when I have complicated cross section, what way the shear force will show up when I have to calculate, if I have to solder, if I have to join, I will have to find out what way the shear stress shows up. And you have to get the conceptual understanding, and we take a horizontal section. We are very clever. I will ask a question, counter question later, that you will have to do some thinking at home and then come back. See, the board is not smart. Suppose I make the board smart, what would happen to this? Do you realize that there is force imbalance in this? My diagram is not complete. We know from the physics of the problem, the beam as a whole was in equilibrium. Suppose I make the board smart, this element will not remain in place, it will only have a translation. Fine. It will keep on going in that direction. I have stopped it at some position, the board has become inert. Okay. So, that means to keep this tied in this place, I should have stresses developed at the bottom of the surface. Is the idea clear? It is a very subtle point. You have to appreciate this. And you will also have to appreciate why I have put this in the negative direction. It has moved this way, I should have put it in the positive direction, is not what you normally will feel. And we are looking at the negative phase. On a negative phase, negative direction is positive. We are developing basic equation. Okay. So, unless you have shearing action initiated there, this cannot remain in equilibrium. Once you have understood this, we will go back to our rigid body mechanics, sigma fx equal to 0, sigma m equal to 0, all that we will do. So, that is how you go back between rigid body mechanics and strength of materials, that is deformable solids. So, we are actually building a firm building on foundation. So, you cannot afford to forget concepts in rigid body mechanics and even the concept that we have developed all through the course till today. All that is needed for you to appreciate how the shear stress is developed in the beam. So, considering the forces in the x direction for equilibrium to be satisfied, let us write the expression. See, we are writing stress components, and if I know the area, I can find out the force. Fine. So, I want to put summation of fx equal to 0. So, we look at what happens at x plus delta x, sigma x into dA at x plus delta x, and I call this area as A1. It is not the complete area of the cross section, it is the area of the cross section above the line which is located at y1. Fine. This section is above the pink section is what we are really looking at. And we have understood that there has to be a force on the bottom surface, and when I write the equation of equilibrium, I must put the sign as appropriate. Fine. So, this is in the negative direction, so I will put it as minus delta fyx, and then this is also, we will have to put what happens at direction x, and so I have this integral A1 sigma x dA equal to 0. So, I have this as when I want to find out what is delta fyx, okay, I have this as integral A1 mb plus delta mb into y, because this is what we have said in the idealization, just use the bending moment at that cross section. So, I can find out what is the stresses there and then multiply it by the area and do the integration from in this area A1 at x plus delta x, and you have force acting on this surface, that is mby divided by izz dA. That gives me delta Fyx equal to minus delta mb by izz integral a1 y dA. What is y dA? It is first moment of area. Okay. So, what we have actually done is, we have recognized that bending moment varies along the x axis, and we have utilized the flexure formula using mb at this cross section, using mb plus delta mb at this cross section, and we realized because the bending moment is different, the stresses are different on this, consequently the forces are different. So, in order to keep the element in equilibrium, I should have stresses developed at the bottom surface. I have shown this as force. Force give rise to stresses, okay. And then our interest is to find out this. And now we have got the expression delta Fyx equal to minus delta mb by izz integral a1 y dA. Still, we have not seen that this expression is written in terms of the shear force V. And in the limit, what we would do? We would make delta x go to 0. Okay. So, that is what we are going to see in the next step, and you divide this by delta x and you put the limits, delta x goes to 0. So, I get this as d Fyx divided by dx equal to limit delta x tends to 0, delta Fyx divided by delta x equal to minus dmb by dx 1 by izz y dA. See, I have been able to take out this because I consider the beam has a constant cross section made of one material, that is also I am conscious about it. And y dA you can easily calculate, and we will also replace this by q. Can you tell me how I can bring in the shear force here? Is there anything that you know from your earlier development of the subject? You can be louder. Equality of cross shears we have discussed to say that this is equality of cross shear is one idea, because what she is trying to say is, if I have stresses developed at the bottom surface, I should have stresses developed in the in this surface also. So, I essentially have, if I have this as x plane, I will have tau xy developed, and I equality of cross shears, whatever the tau xy developed, I will have tau yx, that is fine. But now I do not want to have this expression having bending moment, I want this expression to have my shear force. You know, I have discussed it in the last class. I have shown you what is the interrelationship between the load applied and the shear force, and the bending moment applied and the shear force. So, if I invoke that condition, I will have this as dmb by dx equal to minus v, and then I can write dFyx by dx equal to v by izz integral a1 y dA. See, shear stress distribution in beam is subtle to understand, and it also requires all that we have developed as part of the course. You cannot directly jump and then see how. Maybe you can memorize the final expression, that is not going to add to your understanding and knowledge. Okay. Memory is secondary. You have to appreciate how the subject is developed. So, I have this small area shown, and then I will also write the integral properly. Okay. I have this at a distance y, and this is area A1, and we will also see dFyx by dx equal to v by izz integral a1 y d. Y dA is the first moment of area, and usually it is given a symbol q. Q is taken as integral A1 YD. You do it about the area A1. And you also have coined another terminology. Fyx is a force per unit length. You call this as shear flow. Why you call it a shear flow? We make an analogy to fluid flow that we would see when I take an I section and then see how the shear is transmitted. We will say two flows come, join and then go like this and separate out. So, this is force per unit length. And suppose I know what is the width of the beam at this cross section, suppose I take this as B, I can also find out the shear stress. And we also assume that shear force is uniform across the beam. See, all that you can do as part of your development, but final results that we have got should conform to an exact analysis like what you do in theory of elasticity or a carefully done experiment. It should satisfy both of this. Then our analysis is correct. So, I have tau Yx equal to Q Yx by B. That gives me a very important relationship, that is equal to VQ by BIZZ. And you should understand what is the symbolism. Q is integral A1 by dA. Suppose I want to find out what is the variation of shear stress over the depth of the cross section, I must find out for a generic cross section, write the expression and integrate it for the entire this one. Okay. For each cross section I should find out, each cross section I should find out what is Q. Suppose I am able to have a simple cross section, then if I write for a generic cross section, that itself can be extended to give you for what happens in the complete cross section. Okay. So, shear stress evaluation is very subtle and you have to keep calculating Q for every cross section you look at. Here we have taken a cross section which is symmetrical about the xy plane. The edge is not straight. I have taken a small deviation in the edge to just to give you an idea. We are only insisting on symmetry along a plane. The shape is immaterial in our theoretical development, but when we do the problems, we will take that as a rectangular cross section or an I cross section or a circular cross section, for which you can easily calculate the mathematics. And we will also illustrate what way the flow happens. And here you understand and bring in, on the top surface, can I have any shear stress? Even though this cross section transmits shear force, we have said the shear force distribution should be such, it should go to 0. Can you tell me whether it goes to 0 on the basis of this expression? Can anybody see how it goes to 0 on the top layer? What happens to Q on the top layer? Is the question clear? See, I have taken y1, I will increase the y1 to middle of the section, I will increase y1 to the top of the section. When I put it at the top of the section, what is value of Q? Q is 0. You get the point. I start from that, so there is no area to start with. The area builds up only when I have some sufficient thickness. So, what we conjectured based on free surface is also mathematically seen. So, our mathematical development is correct. Now, I put the shear flow from this, I show this as a bigger arrow because my Q is larger here. For the next one, from the illustration point of view, how do you expect the arrow head to be? Is it going to be small or bigger? Because when I show this, I can show it with few arrows as an illustration. When I put the arrow of one size here, what would be the arrow that I should put next? Is it going to be smaller or bigger? Is the question clear? That means I have found out what is the shear stress at this cross section. Now I have moved up. You can even say that I have moved up by this distance, the height of the arrow. There Q becomes smaller. When Q becomes smaller, your shear stress also becomes smaller. So I will have a small arrow, and when I go to the top, it is almost close to 0. And what happens on the bottom surface? I will have a shear flow like this. Please make a sketch, because these are all conceptual appreciation. See, conceptual appreciation is what is going to stay with you, because tomorrow you take up a problem which is challenging, your mind should think and simplify the problem. To aid your thinking process, I go slow, show what are all the interactions that happen, and then appreciate that it satisfies all that what you have developed earlier. That gives the comfort that the logical step that we are taking is in the right direction. See, if I had taken the problem as a boundary value problem and solve the differential equation, follow all aspects of mathematics, that is good enough to see that you have got the solution. But surprisingly, even though I say theory of elasticity gives you exact solution, the exact solution available are practically for a very few problems. That is the reason why in strength of materials we put lot of emphasis on physical appreciation and the thought experiment, looking at the experiment, simplify the problem so that you get the idea of how the system is responding. So the procedure what we have taken is not fully mathematical. We use mathematics in between, and in order to verify that our steps are correct, we look at the experiment whether our statements are right. Then we say the next step. Final solution we compare it with theory of elasticity. Fortunately, it exists for a rectangular cross section. Fine. Now let us do it for a rectangular cross section, how the shear stress distribution is. Here you can find out Q. You can easily find out Q because it is a very simple cross section. Please make a neat sketch. And if I have to find out Q, I will write it in a generic fashion, because if the cross section is not rectangle like this, then I should do the integration properly. So I take a small strip. This strip has a height of dy. So I will write the expression for a generic cross section. V by Bizz, and I want to have the area is given as B dy. So this I have written it for a representative cross section at y1. Because the cross section is simple, the same expression by substituting the limits appropriately, you can get calculate Q easily. That is what I said earlier. If you have a simple cross section, if you write a generic expression like this is enough to get Q at any cross section of interest. And what is the cross section of interest? The center of the cross section, centroidal section is important, because centroidal section is also a neutral surface. And I have made a argument when we looked at the cantilever that you may have the shear stress reaches maximum at the centroidal plane. So I have this as V by 2 Izz, tau xy is given as h by 2 whole squared minus y1 squared, and I have to put the limits appropriately. I have gone from y1 to h by 2. At the top and bottom fibers Q equal to 0, so in shear stress is 0. Now what happens at the center of the cross section? Q becomes B h squared by 8 because y is 0, and you get the tau xy max as V h squared divided by 8 Izz. And what is the nature of variation? See, in the case of uniaxial tension, the stress transmitted was uniform across the cross section. In the case of twist, we found the shear stress was varying linearly. In the case of bending, the bending stress was very linearly. There is a difference. This is a function of, it's a parabolic function. You get the idea? So, it is non-linear, and when I do it for the center, that is what is shown, and I have this as a parabola. So, this is non-linear, and on the top surface it is 0 and the bottom surface it is 0, and it is a maximum at the centroidal plane, which we have also seen long time back when we discussed the free surface. I took a generic 3-point bending, and there the argument what we put forth was, I take a section and these are not loaded boundaries, and I said I can find out what happens at this top point and bottom point, and our logic was, it was a free surface, there is no shear acting on that, and we said that this shear force is not acting because it is a free surface. So, all the other shear stresses go to 0, and we also raised a question, can it support a horizontal force in this plane? All that is happening in the cantilever beam as well as this 3-point bend beam. We have seen shear stress is 0 at the top point and at the bottom point, and at the top point and the bottom point you have the maximum normal stress. So, this conforms to that understanding, and I have also said I have a cantilever beam, and I asked you to observe what happens to the centroidal axis, whether it is remaining in a black color. It was not black color, it has acquired a color. See, experiment whether the value is small or big, it is truth. Right now what we have discussed is, what is the variation of shear stress? We have not commented about what is the magnitude of shear stress in comparison to bending stress. The focus is only on the variation, and I have asked you to look at two aspects. One is the centroidal axis is having a color, and second one is this fringe is not a straight fringe, but it is having a curvature. Can you tell me what is the state of stress at a point like this? Because the beam is transmitting both shear force as well as bending moment, what is the state of stress at this point? Can you tell me? You understand? What are the stress components? See, flexure formula gives you bending stress, and then we have evaluated even shear stress. I have taken a generic point here. Fine. It is something like some point in the, it is below the surface. See, you are looking the side view. Okay. If you look at from the cross sectional point of view, it is some point just below like this. It can even be taken as y1. So, I will have shear stress here. I will also have bending stress. So, if I put that, stress tensor is sigma xs tau xy tau yx 0. Is the idea clear? And what you have here is your sigma xx is varying linearly, and your bending moment also in a cantilever beam varies linearly from this loading point to the fixed end. But I have this, rather than being a straight line, it is curved. Where does that curvature come from? You know, photoelasticity plots only sigma 1 minus sigma 2, and you are putting tau xy is non-linear. So, your variation of sigma 1 minus sigma 2 is not linear over the length of the beam for an horizontal line. Okay. So, you have this as a curvature. Okay. Now, let us look at the relative magnitudes of bending and shear stress. You know, you have a rectangular cross section, and you have shear force and bending moment diagram, and where do you have the maximum bending stress? You have the flexure formula here. I have the maximum bending moment is PL by 4, that happens here, and I can have this as a maximum tensile stress. You can easily calculate. The I for this is BHQ by 12. So, if I do this, I get the sigma max as 3 by 2 PL by BH squared, and you also know the expression for tau xy. For a rectangular cross section, the maximum shear stress is VH squared by 8 IZZ. When I substitute IZZ, I get this as 3 by 4 P by BH. So, this gives a comparison. That comparison is listed in the next slide. And the ratio is 1 by 2 H by L. And we want to have a slender beam. The depth should be much smaller to the length of the cross section. Okay. Normally you have this as 10. So, shear stress is at least 20 times smaller than the bending stress. Isn't it surprising? Okay. Many books, what they do is they give you the picture like this. They don't go and emphasize what is the relative magnitudes. I have drawn these stresses in a very big picture for me to illustrate the point. So, this is for the case of a rectangular cross section subject to 3-point bending. That means it has a constant shear force and a variable bending moment. And suppose I plot to some scale the stresses, the way the beam is bent. I have the top surface is compressive, bottom surface is tensile. Is the idea clear? And many books simply put the shear stress variation. The focus is only on showing that this is a parabola. Fine. And you get duped that shear stress magnitude are comparable to tensile stress magnitude. That is what you carry. When you look at a picture, the same thing I discussed when you are looking at stress strain curve in the tension test. I focus that you have to give importance to the level of strain. On similar lines, suppose I plot to scale what is the shear stress, hardly anything. Look at this and look at this. In many of our studies, we will consider shear stress magnitude small, we will ignore it. Even in your deflection, we will ignore in many of the problems. There is justification. When it is important, you have to worry about it. That we will come to it, because we have still not discussed what happens near the load application point. And there are also many things that you can learn from this. Fine, I want you to make a neat sketch of this. This is a very, very important slide. It gives you a lot of conceptual understanding. Can you tell me what is the stress tensor here? I want you to develop. See, by Flexure formula, you get only component of stress. You should know how to write this as a stress tensor. Minus sigma xx 0, 0, 0. And can you tell me what is the stress tensor here? It is tensile. So, it is sigma xx 0, 0, 0. What is happening at the center? 0 tau xy 0. What is happening at in between point? It is sigma xs tau xy tau x 0. In terms of principal stresses, I will have this as sigma 1, sigma 2 on this for this point, no problem, because this is done in algebraically larger and one is labeled as sigma 1, algebraically smaller is put as sigma 2. Suppose I come to the top surface, can I write like this? I cannot write. This becomes sigma 2 and this becomes sigma 1 because this is compressive. Okay, so it is a very, very important conceptual slide. So, in this class, we have looked at how the shear stress is developed. It is a very, very important and subtle concept. We have looked at an actual experiment and understood if I have multiple layers of the beam, we could identify that is slipping happening. That indicates what is the shear stress possibility. Then we have also learned how to calculate the shear stress. We have found that it is 0 on the top and bottom surfaces, reaches a maximum at the centroidal plane or at the neutral surface, okay, whichever way we have to look at for problem to problem. Thank you.